All right, guys, today we're beginning a new unit on logarithms, which is kind of a long word, so usually we just call them logs. And logarithms, the type of function itself would be one of the least important functions we've learned all year, because it turns out there aren't a ton of real-world things. There are some things, but there's not a ton of real-world things that are logs. The thing that makes logarithms important is that they are the inverse of exponential functions. And exponential functions are really important. We saw how much they had to do with money and growth, and they come up all over the place in the real world. And we will be able to use the inverse of exponential functions, logarithms, to solve exponential equations. But first, we need to learn a little bit about logs before we can do that. So, log, the way we read this is we write log, and then you'll see there's a number lower down. That's called the base of the logarithm. And then there's a number that's the same height. It looks kind of like an exponent on a, but it's the same height as the log. This is called the argument. And the way we read this is log base a of b. So log base a of b. So the base is a. We say log base a of b. And it means, it asks a question. It asks, what exponent do we need to put on a to get to b? Or another way of thinking of that is a to what power gives you b. So this little one, I like to think of it as if there's like an invisible missing exponent sign that we need to figure out what goes there. A to what exponent will give us b? And you can see how this is related to exponentials already, I think. So let's do a couple examples. So this is like the key thing of the day already, guys. It's right here. You definitely want to make sure you have this in your notes somewhere. Let's do some examples. So log base 2 of 8 is how we read this. Log base 2 of 8. And it asks, what exponent needs to go on 2 to get you to 8? 2 to what power gets you 8? So what power do we need to put on 2? Well, the answer is 3, because 2 to the third power means 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. So 2 to the third power is 8. And that is the answer to the logarithm. The answer to the logarithm is what exponent we needed to put there to get to 8. Why don't you guys try a couple of these? Try log base 3 of 9. Log base 5 of 125. Log base 2 of 16. And see how we do. Hopefully we got log base 3 of 9. 3 to what power? What exponent needs to go on 3? 3 to what power gets you 9? And the answer is 2. 3 squared is 9. How do we read this one? Well, this is log base 5 of 125. And 5 to what power gives you 125? If you're not sure right away, one thing I like to do is just start multiplying a bunch of 5s together. So 5 times 5, that's 25. Times another 5, so 25 times 5. You can even use a calculator here. 25 times 5 is 125. So it took 3 5s to multiply together to get 125. And so the answer is 3. Log base 5 of 125 is 3. How do we read this? This is log base 2 of 16. Notice the 16 is the same height as the log. It's not higher than it. The 2 is lower down, but the 16 is the same height. And it's saying 2 to what power gets you 16? And the answer is 4. 2 to the fourth power gets you 16. 2 to the fourth power is 2 times 2 times 2 times 2. So you don't need to write this down here if you can do it in your head. The answer is the exponent you needed to put on 2 to get to 4. So hopefully we feel good about that. Sometimes evaluating these logs can look a little bit different, like log base 7 of 1 over 49. Log base 7 of 1 over 49. This is saying 7 to what power gets you 1/49th. And I hope we notice that the key thing here is that it's got this 1 over, and we're looking for what exponent could make it be 1 over. Well, what kind of exponent makes it be 1 over something? It needs to be a negative exponent. 7 to a negative power will be 1 over whatever the thing is. So the exponent is going to need to be negative, and then 7 to what power gets you 49? Well, that's just 2. So the answer is negative 2, because 7 to the negative 2 power means the negative exponent tells you it's 1 over 7 squared, so 1 over 49. So whenever you have a fraction, it's usually going to need a negative exponent. Why don't you guys try one of these on your own? Why don't you try log base 3 of 1/27th? And hopefully you saw that this was going to be a negative exponent, because 3 to a negative power will be 1 over. And then it's 3 to what power gets you 27? Well, 3 to the third power. 3 times 3 is 9. That's 9. Times 3 is 27. So you need 3 3's multiplying together to get to 27. So the exponent we needed here was a negative 3, a negative to make it 1 over, and then 3 to the third power is 27. So hopefully we're feeling okay about that. Another kind of tricky thing is, what if it's like log base, I don't know, 64 of 8. So this is saying 64 to what power gets you 8? And it is not going to be negative. We can tell it's not negative because it's not 1 over. But I notice it got smaller. So how on earth am I going to make an exponent to make it get smaller? Well, remember that fraction exponents are roots. And in this case, the answer is, so if it gets smaller, you can think, ooh, is there a root, either like a square root or a fourth root or a cube root? Is there a root that I can do to get down there? And here, the square root of 64 is 8. Or you could think like 8 to what power is 64, and it'll be that root. So 8 squared is 64. That means the square root of 64 is 8. So we need this to be a square, we need it to be square root of 64. Remember, roots are fraction powers, and the square root is the 1/2 power. So the 1/2 power is the answer here. So why don't you guys try one on your own? Log base 8 of 2. And hopefully here you can see that it's not a negative, but it did go down. So it's going to be a root. So what root can we do? Well, 2 to what power gives us 8? 2 to the third power is 8. And so the cube root of 8 gives us 2. And what power is this? Well, this is the 1/3 power. This is 8. Sorry, this is a 1/3 power. 8 to the 1/3 power means the cube root of 8. And that is 2. So the power, the exponent that we need on 8 is 1/3. So hopefully you feel good about that. Guys, if you're struggling on this, you might want to go back to our previous unit, lesson 7.3, the first half of that. Like if you don't know what I'm talking about these like negative and fraction powers, you might want to do lesson 7.3, at least the first half, right? It's where we really went into depth on these weird powers. And logs don't go well if you don't know this. We are going to have a mastery quiz on this stuff coming up soon. All right, let's try a couple more weird ones. What about log base 25 of 1/5? Okay, what's going on here? Well, I know that the exponent needs to be negative because of the 1 over. A negative power, 25 to a negative power, will be 1 over. But then we need to end up getting down to 5, right? So how do we go from 25 to 5? And just like before, it's getting smaller, so we need a root. Well, the square root of 25 is 5. So the way we do the square root of 25, we want square root of 25. And the way we do that is with a fraction power. This is the 1/2 power because the square root is the 1/2 power. So 25 to the negative makes it 1 over. And then the 1/2 power is the square root of 25, which gets you to 5. So tricky stuff here, guys. Why don't you guys try one of these on your own? Log base, let's see, 16 of 1/2. Log base 16 of 1/2. And hopefully you noticed that it's a fraction, so we're going to need a negative exponent. That'll do the 1 over. That'll take care of the 1 over part. And then how do we get from 16 to 2? Well, it's getting smaller, so it has to be a root. It's going to be a fraction power. And 2 to the 4th power is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. That's 4 2's multiplied together to make 16. And so the 4th root of 16 gives you 1/2. And so to do the 4th root, that's the 1/4 power. Okay. All right, hopefully we feel okay about that. I'm going to do one more tricky evaluating logs, and then we're going to move on. How about log base 4 of 8? Okay, well, I see it got bigger this time, right? But 4 squared is already 16, so that's too big. Sometimes if it needs to get bigger, but doesn't need to get, like, it's not a whole number, it might end up being a fraction power, which means like you want to look and see, can you do a root of this? Can we do the root of 4? Yes. We can do the square root of 4. The square root of 4 is 2. And then can we get from 2 to 8? Yes. 2 cubed will give us 8. And so the square root of 4 cubed will get us to 8. So sometimes you need to see, can you do a root of the base to go down, to like get down? So you want to go down to 2, and then do it to a power to get back up. And so the square root of 4 cubed is the 3/2 power. The half power is the root, and then the third power is cubing it. And so, you know, sometimes we can go back down and then come back up. Let me give you guys a chance to try this. Try it, log base 27 of 9. And so here, you know, 27 to what power gets you 9? Well, it's getting smaller, so I might think root. So like, what root of 27 can I do? I can't do the square root. There's no number times itself that gets you 27. But I can do the cube root of 27. What times what gives me 27? That's 3. So the cube root of 27 is 3. And then I can go from 3 to 9 by doing it squared. So, this is the cube root squared, and so the power, that's the same as 27 to the 2/3 power. Remember, the denominator is what root it is. So 27 to the 2/3 power gives you 9, and so that's what that log is equal to. All right, guys, there are 2 special logs you need to know. These are, one of them comes up a ton in science, and the other one is like the only log that anybody uses in math after algebra 2. Not the only log, but like it is, I don't know, 9 times as common as all the other logs. So the one that is used a lot in science is log base 10. There's a lot of cool things you can do with log base 10, and it's important enough that in science, so if you want to do like log base 10 of 1,000, right, this means 10 to what power gives you 1,000. And so remember, when you're multiplying tens, it's just how many zeros it is. So 10 times 10 times 10 is 1,000. So you need 10 to the 3rd power. 10 times 10 times 10 is 1,000. There's 3 zeros there. So log base 10 of 1,000 is 3. But the way we would write this is a special log, is we actually just write log of 1,000. If, and I'm going to write this in green because this is important, if there is no base, it is automatically base 10. Okay, so this is automatically log base 10. So this automatically means log base 10 of 1,000. Okay, so a lot of times you'll see that. Let's try that. Let's try log of 1 over 100. Okay, so you'll notice there's no base here. So what's the base? It's 10. So you can think of this as like an invisible 10 here. So it's saying 10 to what power gets you 1 over 100? Well, hopefully you realized it needs to be a negative to do the 1 over. And then 10 to what power gets you 100? 2. 10 squared is 100. So 10 to the negative 2 power is 1 over 10 squared, which is 1 over 100. So if there is no base, it's automatically log. If there's no base on log, it's automatically base 10. Okay, so that's important. The other one is ln. This is an L. It's a lowercase l. Sometimes people think it's like an I. It is not an I. Okay, this is an L. It actually stands for log. Okay, log, and the N is natural. That's where it's coming from. And it, you guys might remember we learned a special number that is called the natural number. What is the natural number? I hope we remember that the natural number is another name for E, which is about 2.7182818284590, whatever. And so when it's ln, they will never write the base. It is automatically base E. And the reason it's backwards is because the people who were using these logs first weren't English. It was the French. So it was logarithmique natural. It's the same as in Spanish. It's logaritmo natural. So that's why the ln it's not in English. We read this. This is the natural log, and in this case, it's of 5. So the natural log of 5 means log base e of 5. So it means there's automatically a base e there if they write ln. And the way you read it is the natural log of 5. That's how you say it out loud. And it's saying e to what power gives you 5. Guys, e is a weird number. We consider this simplified. It's going to be 1 point something. So there's a button ln in the calculator. So if you need a calculator ever, you can do it. Ln of 5, it's going to be 1 point something, but it's going to be irrational. So logs of any whole numbers are going to be irrational. But there's some cool things we can do with ln. Like we could do natural log of 1. We haven't done an example like this. This is saying e, remember there's like an invisible e here, e to what power gives you 1? What is the natural log of 1? Well, it's 0. Anything to the 0 power is 1. Now, this is actually the same as if I did log of 1, because 10 to what power would give me 1? That would also be 0. Or log base 53 of 1. That would also be 0, because 53 to the 0 power is 1. Turns out the log of 1 will always be 0 no matter what the base is. So that's one special thing that happens with e. Another thing that might happen is natural log of e squared, or something like this. So this is saying log base e of e squared. It's saying e to what power? E to what power gives you e squared? So remember, there's like an invisible e here. That's the base. E to what power gives you e squared? And the answer is going to be, like, what number needs to go here? Well, 2. E squared. The answer is 2. E to the 2 power gives you e to the 2 power. So those ones come up sometimes. All right. We're going to stop on evaluating logs. I'll let you practice a couple real quick with mixed practice. But let's move on to changing forms. So it turns out it's useful sometimes to change forms. So let's do 3 squared equals 9. This is called exponential form. And there's a way to rewrite this as a log equation. It's kind of like if you're writing 5 times 2 equals 10. This is multiplication, but we could rewrite this as a division. We could rewrite this as 5 equals 10 divided by 2. That's just another way of saying the same fact written differently. We can do the same thing here. We can write this as a log equation, and the log and the exponential will always have the same base. So if the exponential has a base of 3, the log will have a base of 3. And these two ones will switch, and I'll show you why in a second. So log base 3 of 9 equals 2. The reason is this is saying 3 to what power gets you 9? Well, right here it just told us the answer. 3 squared gave us 9. So 3 to what power gives us 9? The answer is 2. So this is called logarithmic form. So logarithmic form. And we can go back and forth. So similarly, I could take, log base 5 of 125 equals 3 and rewrite it in exponential form. And again, we know how it's going to work. The base of the log is going to be the base of the exponential. So 5 is going to be the base of the exponent, and it's going to be to this power. So 5 to the 3rd power equals 125. You'll notice that the 3 and the 125 kind of switched when we went from exponential to log form. And this should make sense, right? This is asking us what power needs to go on 5 to get to 125. The answer is 3. So 5 to the 3 power gives us 125. This will be useful next class when we get to our properties of logarithms, which will be super useful. The last thing I want to end this video really quickly, but before I do, I want to talk about estimating logs very quickly. Let's do log of 20. What base is this? What is the base of this logarithm? I didn't write it. So the base is automatically 10. And so it's saying 10 to what power gives you 20. And this is an irrational number. Just like when we did, natural log of 5 and that came out to be a decimal, this one will be 2. There's actually a button in here for log of like this log, if you don't press anything, automatically means base 10. So this means log base 10 of 20. And so it's saying 10 to what power is 20? And so we can estimate it by saying, look, okay, 10 to the 1 power is 10. 10 squared is 100. So this exponent is too small because 10 isn't 20 yet. And this one is too big, right? Because 100 is bigger than 20. And so the exponent has to be somewhere between 1 and 2. Like, I don't know, maybe it's like 1.4. I don't need you to be able to tell exactly what it is. You just need to know it's between 1 and 2. If you said 1.7 or 1.3 or 1.1, I would give you full credit for any number that is between 1 and 2 here, because I know that 10 to the 1 power is 10. That's too small. And I know that 10 squared is 100. That's too big. And so the answer is going to be 1 point something. It's 1.3, right? Like, and I don't expect you to know it. I don't know that. But, you know, you should know it's between those two things. Let's practice one of those real quick. What about log base 2 of 10? Okay. So this is saying 2 to what power gets you 10? What is this about? And I hope you said it was something like 3 point, you could have said 3 point anything. And the reason is because 2 to the 3rd power is 8. That's still too small. But 2 to the 4th power is 16, and that's too big. And so it must be 2 to the 3 point something to get us 10. So, you know, we can estimate logs. So if you said like 3.3, whatever, you're going to get full credit, right? So there's actually a way to do log base here. Log base 2 of 10, let's see what it's equal to, 3.3. 3.32. It's an irrational number. You can't find exactly how much it is, but you can estimate in your head that it's between 3 and 4 because 2 to the 3rd power is too small, 2 to the 4th power is too big. All right, guys, with that, I think we're going to stop for the day, and hopefully you feel good about, you know, this beginnings of logs. We really are. The key thing about logarithms is that we're going to use them to do the inverse of exponential functions. So our next unit after we learn about logs is to go back and solve exponential equations. And it's just asking you what exponent goes on the base to get to this. Have a good rest of your day, guys.